lecture, I would like to introduce Professor Sven Hansbo from Sweden. He is now Emeritus Professor in Geotechnics at the Chalmers University of Technology in Sweden. Sven is the former president of Swedish Geotechnical Society. He was the chairman of the International Conference in Soil Mechanics and Foundation Engineering 1981 in Stockholm. Professor Sven Hansbo has been involved with the whole life with the theory of vertical drain piling, especially the sediment reducing piles. Professor Sven Hansbo's first visit to Vietnam was in 1979. It's very more than 30 years ago. And he has 3 Vietnamese doctoral students, Professor Tien, me, and Dr. Zu Thị Tien.
And organic soils, for example, gyttja and peat, we have been using electroosmosis, vertical drainage, and deep mixing. I have been involved in the keynotes carried out by the European Eurocodes, and we have been helped by the Japanese in these projects. There are Eurocodes, both regarding vertical drainage and deep mixing. Now, I want to show you some of the... Oh, I'm sorry. The first thing regarding the clay soils and organic soils is to determine the compression characteristics of the soil. And this is usually carried out by the aid of odometer tests. In some cases, we can also use triaxial tests in which no radial deformation is allowed to take place. The samples utilized for odometer tests are usually taken by means of piston samples and should be as undisturbed as possible. It is very important to find the correct value of the pre-consolidation pressure. As you can see here in this picture, it's very important to know exactly if the soil is normally consolidated or if it is over-consolidated. And this is carried out by means of a odometer test, as I show you, because there you can determine the pre-consolidation pressure in the soil. Coefficient of consolidation in horizontal pore water flow and not only in vertical pore water flow, which is determined in the conventional odometer tests. And the linear presentation could be presented in this way by the method determined by Selfors in his doctoral thesis. There is also another possibility to check the value of the pre-consolidation pressure determined by odometer tests, namely on the basis of undrained shear strength and liquid limit. So we can find that the pre-consolidation pressure of the soil is equal to 2.22 times the undrained shear strength divided by the liquid limit value. That shortens the drainage paths created by the excess pore water pressure caused by loading. You will have a pore water flow in horizontal directions towards the drains. And this is usually well, if you have drain installations in thick clay layers, the hydraulic gradient in horizontal direction towards the drains will be much larger than in the vertical direction. The consolidation process will thereby be considerably accelerated. In the theoretical analysis of the effect of vertical drainage, each drain is assumed to dewater a circular cylinder, soil column, whose volume equals the parallelepiped formed by 4 neighboring drains in 2 adjacent rows. In order to make this parallelepiped coincide in the best possible way with the circular cylinder, the drains are mostly installed in equilateral triangular pattern. This yields a diameter value of the column dewatered by a drain, 1.05 times the drain spacing. If the drains are installed in square pattern, the D value will be 1.13 times the drain spacing. Drains is almost equal. You see, the one important thing is the permeability of the vertical drain in longitudinal direction of the drain. And that is called the discharge capacity of the drain, and that should be really high enough so that the drainage will effect in the way you expect. The excess pore water pressure in the area surrounding the drain is, of course, affected by preloading. We can put very high load on the soil surface to guarantee that you have a very high excess pore water pressure, which causes pore water to flow into the drain. But you can also use a vacuum method, which is another method of causing excess pore water flow to, or the pore water flow to take place in the direction towards the drain. This is a matter which is one of the favorite problems I work with. In the middle of the 19th century, the French engineer Darcy discovered that the rate of flow V in water-saturated sand followed the simple relationship. The flow water is equal to the hydraulic permeability times the hydraulic gradient. Darcy's law is generally considered to be valid for laminar soil flow in all types of soil. However, the deviations from Darcy's law have been found to occur in clay soils at small hydraulic gradients. Considering the character of the internal forces in the pore water, electric double layer forces, absorption forces, etc., it is logical to assume that the porosity of the clay would seemingly increase up to a certain point with increasing hydrodynamic forces. This has been observed in several experiments. So this is one of the main, shall we say, the main interest I have in vertical drainage, to show that this is really the case which one has to take into consideration, the deviation from Darcy's law. I call it either non-Darcian flow or exponential flow. And you can see here that you have, this is the type of correlation between flow and hydraulic gradient, which has been found in these experiments. And you can see here that these values of I0 and IL, in the test I carried out in my doctoral thesis, showed that I0 was approximately 1 to 3, and IL was approximately 5 to 6 or something, and this leads to an exponent equal to 1.5. On validity of Darcy's law. And this is the consolidation carried out by the aid of non-Darcian flow. And here you see the coefficients used in this solution based on non-Darcian flow. But of course, there is also a solution based on Darcy validity of Darcy's law. And these are all given in the paper, which you find in this presentation. It is, I don't want to discuss these equations, because these you can try to find yourself in the paper. There is also the excess pore water pressure, which is produced by the loading of the soil and the vertical drainage. And you have here the equation based on validity of non-validity of Darcy's law. And this is the excess pore water pressure based on validity of Darcy's law. And because when you study the effect of vertical drainage, you usually you measure the sediment at various levels in the soil, on ground surface and at different depths. And you measure also the pore water pressure created by loading of the soil. And these are conventional methods of studying the effect of the vertical drainage. I will come back to that later on, so you can see the difference you can have in the two methods. There is a correlation. Lambda is the coefficient of consolidation in Darcian flow, and C sub H is the coefficient of consolidation in Darcian flow. And you can find the correlation between these two coefficients of consolidation in depending upon the hydraulic gradient created by the loading operation. If you take into account also the vertical flow of water in one-dimensional consolidation, the two equations, non-Darcian flow and exponential flow, or shall we say Darcian flow and exponential flow, are just corrected in this simple way. I'll come back to that later on also. Because here you use, in both cases, you use the validity of Darcy's law when you study the effect of the pore water flow in vertical one-dimensional direction. This is a case which is rather interesting. The test field at Squiredy, 25 kilometers west of Stockholm, was established in 1957 by the Swedish Geotechnical Institute by order of the Swedish government for the purpose of finding if the place was suitable for a new airfield. All test areas were provided with sand drains except one, test area number 4, which you can see on this picture. The draining operation was carried out as follows. First, the topsoil was removed to a depth of about 25 centimeters and replaced with sand and gravel about 50 to 70 centimeters in thickness, on which the drainage equipment was to be operated. A hollow mandrel of steel, 14 meters in length. You can see the depth of this soil here is a maximum 14 meters. But so we had hollow mandrel of steel, 14 meters in length, 15 centimeters in inner diameter. It was driven down by means of a pile driver with 1,200 kilograms hammer and a maximum fall of the hammer of 0.5 meter of the working table, and was then withdrawn, leaving a sand column of about 18 centimeters in diameter in the clay. Test area number 3 is 35 meter diameter with 1.5 meter drain spacing and an overload of 2.2 meter of gravel. To take precaution against possible slides, this area was surrounded by loading berm, 12 meter in width and 0.7 meter in thickness. And test area number 4 is 35 meters in diameter and undrained with an overload of 1.5 meters of gravel. Vertical and horizontal settlement observations and pore pressure observations were carried out in order to study the average vertical consolidation. The settlement observations were carried out at the ground surface and at depths of 1.5, 2.5, 5 meters and 7.5 meters of depth. The load placed on test area number 3 was reduced 1.5 meters of gravel after about 3.5 years. The use of sand drains can be associated with certain limitations. The sand for the drains must be chosen with great carefulness to ensure that the discharge capacity of the drain is high enough. The diameter of sand drains used internationally vary often from 16 to 50 centimeters. The installation of sand drains with mandrel closed at bottom can cause vertical cracks in the clay surrounding the drain, which are filled with sand when the mandrel is withdrawn. This can reduce and increase of permeability in the remoted zone. To reduce the disturbance effects caused by drain installation, prefabricated sand drains with a diameter of 5 centimeters, so-called sand wicks, enclosed in geotech style, exist. Here you can see one of these sand drains installed at Skådeby, and you can see now that when the mandrel is withdrawn, the sand, which was 4 meters above the surface of this gravel, has now been reduced because the diameter of the sand is increased when the mandrel is withdrawn. Here you can see the results of observations. The top curve there is the undrained area, and the one where you can see that the settlement has more or less been limited now, and no further settlement more or less, is the area where the load was reduced after 3.5 years. Here you can see the analysis of the undrained area. And what you see here is the recession after 1.5 years and after I cannot see now, but it is
14 years.
Yeah. And the unbroken line is representing non-Darcian flow, and the broken line represents the validity of Darcy's law. The analysis has been carried out on these assumptions. You can see here the validity of Darcy's law and the non-Darcian flow, the correlation between hydraulic gradient and flow velocity, used in the analysis of the undrained area. And here you can see, after a very long time, that the assumption based on non-Darcian flow has a much, much better correlation between observations than the assumption based on validity of Darcy's law. So this is obviously quite clear that there is a deviation from Darcy's law in this type of soil. So the sorption forces and the electric double layer causes this difference in behavior between flow and hydraulic gradient. Here you can also see a comparison between the observations and the analysis X squared B. And you can see here that the coefficient of consolidation lambda has a much, much better agreement with the observations than the coefficient of consolidation in Darcy flow, C sub H. So this is again a confirmation that there is a deviation from Darcy's law, which one should use in the analysis of vertical drainage. Here you can see membranes, or PVDs, as some call these drains, prefabricated vertical drains. And there are a number of vertical drains existing. The first one was invented by Shellman. It was called cardboard wick, the cardboard wick. And he used this installation already very early in the 1930s. He was the managing director of the Swedish Technical Institute. He also invented a drain installation machine for the cardboard wicks, patented in 1939. And nowadays a great number of prefabricated drains exist on the market. You can see there are several. These are presented in the Eurocode on prefabricated vertical drains. Here you can see an installation of prefabricated vertical drains to a depth of 40 meters in Singapore. So it's a rather big matter, but this was used. The discharge capacity of various types of drains is of course dependent on the depth of drain installation and the size. This is represented by the size of L in the analysis and the permeability of the surrounding soil. If the discharge capacity is too low, a delay of the consolidation process will occur with a maximum value at depth L. If, for example, you have installed drains with a discharge capacity of 500 cubic meters per year in a 20-meter thick clay layer underlain by sand, you can expect a delay in the consolidation process of 1% at 10-meter depth. If instead the soil consists of silty clay, the delay would be about 5%. So it depends very much upon the soil surrounding the drain, of course. And you can see here also that you have very high delays if you have very deep drain installations. And this is L, so it means that if you install a drain in a soil and you do not reach a permeable layer underneath the drain, then at the tip of the drain you will have a very high delay in the consolidation process. A method which is used to determine the degree of consolidation. It is very important to know the magnitude of the primary consolidation settlement. And this can be determined according to Asaoka. Asaoka's method is based on the following procedure. The settlement observed at different equal time intervals, delta t, are plotted in a diagram with Si minus 1 as ordinate and Si as abscissa, where index I minus 1 refers to time t minus delta t and index I to time t. This would result in a linear correlation which extended to Si minus 1 equal to Si gives the value, well, shall I say, which extended to Si minus 1 equal to 0 gives the value of A in this diagram and the inclination angle of the straight line. The primary consolidation settlement is obtained when Si minus 1 and Si become equal. So this is a very simple method of determining the pre-consolidation pressure. Or the end of the primary consolidation, I would say, or the primary consolidation settlement. I will show you some observations made in different test areas. In connection with the planning of a new international airfield in Bangkok, 3 test areas were arranged in order to form the basis for design of soil improvement by preloading and vertical drainage. The result observed in test area TS3 is shown here. The crest width of TS3 was 14.8 meter and the bottom width 40 meter. It was provided with an approximately 10 meter wide loading berm, 1.5 meter thick. The field placed on the area corresponded to a load of 80 kilonewtons per square meter. The drains were installed in a square pattern with a spacing of 1 meter, which yields a D value of 1.13 meter. The monitoring system consisted of vertical settlement meters placed on the soil surface and a different depth and of inclinometers to study the horizontal displacements. It's much better. This is another case, a test field. 125 by 45 meters was arranged for comparing the efficiency of prefabricated vertical bend drains, type geodrain and ollie drain, with that of displacement type sand drains. The test field was divided into 3 sections of equal size with drain spacings 1.1, 1.4 and 1.6 meter in equilateral triangular pattern. The test area was loaded with 2.2 meters of sand and gravel. Load delta Q equal to 40 kilonewtons per square meter. The soil consisted of great, slightly over-consolidated clay, about 8 meters in thickness, slightly organic to a depth of 1 to 2 meters, and barbed with silt seams below a depth of about 5 meters. The primary consolidation settlement calculated on the basis of the odometer compression ratios and an over-consolidation of 5 kilopascal was estimated at 1.1 meter. The settlement process observed in the test sections provided with geodrains and ollie drains was nearly the same. Here you can see the result obtained in the test sections provided with sand drains and geodrains, and using Asaoka's method for determination of the primary consolidation settlement, we find for the section provided with geodrains S primary consolidation equal to 1.09 meter, and for the section provided with sand drains, primary consolidation equal to 1.11 meters. And these values are in excellent agreement with the settlement estimated on the basis of the odometer tests. The analysis of the consolidation process based here on the following assumptions: dW equal to 0.18 meter, and ds equal to 0.36 meter for sand drains, and dW equal to 0.066 meter, and ds equal to 0.19 meter for geodrains. And the relation between the permeability in the undisturbed soil and the remote zone around the zone is equal to 4. L equal to 4 meter, and CV, the coefficient of consolidation of the vertical line undimensional row, is 0.2 square meter per year. Again, you can see that the agreement between analysis and observations is better on the assumption of an exponential flow. Well, the same, I would say, is the case with the Polle test. This is a test in Italy. You can again see, I have very short time now, so I have to hurry on. And you can see again that you have much better agreement between the non-Darcian flow than with Darcian flow. And here again you have from Arlanda, you can see you have a very high overloading in this case, nearly 400 kilonewtons per square meter. And in this case, you can see that there is more or less a better agreement between the assumption based on Darcian flow than on non-Darcian flow, but a very small difference. And finally, I'll show you again a comparison between settlement observations and pore pressure observations. And you can see it is very important that the pore pressure meter, the piezometer, is placed in the correct place. If the piezometer comes too close to the drain, you have a much higher degree of consolidation than according to settlement observations. Therefore, I would say that you have to be very careful when you measure the degree of consolidation observed on pore pressure observations. It is much more reliable to trust the values observed by settlement observations. Thank you very much. This is, I think,
invite Professor Sven Hansbo.
He is my best professor of all the